So if I go in here to our asset loader and I take a look at the load WAV, right, there it is. Somebody was saying that I did a mistype in here. I don't remember which one it was. They were saying that as I was making the header, I got one of the things wrong, perhaps in the format chunk, I think, but I'm not sure which one it was. Valid bits per sample, so it's 2222222. Yes, so block align is 2, and I had it as 4. So thank you for catching that. Saved us a little bit of debugging work here. But yeah, so what we did yesterday is we just kind of started with the basics. We really didn't do anything. All we did was start to copy in the sort of structure of a WAV file in here. And so I'm going to go ahead and kind of pull this stuff up a little bit into the same location as we define our bitmap stuff so that it can be inside the same pragma pack there. Because again, we want to make sure that these are pragma pack 1 so that the compiler doesn't insert any additional spacing. So for example, if you take a look in here, right, these uint16s, they would actually get padded out probably. To be honest, this probably wouldn't have changed. But just in case, I want to make sure that it wouldn't. So I'm going to go ahead and put that in the pragma pack so the compiler doesn't fuss around with it at all. So anyway, what I'd like to do now is I'd like to go ahead and find a way to test this stuff. And so what I'm going to do is I'm just going to insert so that we can start testing and not have to worry about running the game and doing anything in particular. Right when we actually do our update and render call, right at the beginning of that, I'm just going to make it do a debug load wave right there, right? So I'm just going to have it do a loaded sound, like so. And I'm going to have it load some sound out of here, say bloop 00 or something like this. So bloop 00.wav. And that way I can set a breakpoint and have it just kind of, you know, start right out at the code that we're trying to test so that we can, you know, be more efficient about the testing, since presumably we're going to have to debug some stuff and test some stuff, right? So what I'd like to do is I'd like to go ahead and step into that. I wonder if that should actually be the name. Debug load sound. What did I actually call the other one? What did I call debug load BMP? Load WAV. So as I run this, let's just make sure we get the whole file first. We do. And let's take a look at that header and see if we're actually getting something that we think makes some sense. So here is our display here. That size parameter looks theoretically correct. And let's take a look and see if the riff ID makes sense, right? What's R? I don't know what that's. Why is it inserting 2 of those? That's really annoying. When did it start doing that? Who thought that was a good idea? I don't know what that is, but I wish it would stop. Anyway, you can see we have RIFF here, and these are the character codes, and hey, there they are, 42, 49, 46, 46. So it looks like it does go in little endian order like we surmised that it would, so our macro's probably fine too. And then we've got that wave ID there. I believe that's just, what is it, W. So that all looks good, and so our assertions should work. They do. So now all we have to do is actually get down to the business of parsing the actual file, obviously, which is something that we want to be able to do. So I'm going to jump over here to that function, and I'm just going to start implementing it. Now, like I was saying on the other stream, essentially what happens here is you've got these chunks in the file, and those chunks say how big they are. And so what we want to be able to do is we want to be able to have like a convenient, perhaps little cursor that we can kind of move around that will just help us with the bookkeeping of reading through the file. So what I'm going to do is I'm going to have something like a riff iterator. So remember, these are riff file format is the file format that we're talking about. And what I want to do there is I want to have a pointer to some bits, which is just where we currently are in the file. And then I also want to have something that I guess that lets me know what my current riff chunk actually is. And you can see that we've got these sort of wave chunk things here. So I kind of want to have whatever the current chunk is as well, if that makes sense. So let's start off with that. I'm going to go ahead and say, once we parse that header, I'm going to say that we have our riff iterator, and here's our our riff, or I guess maybe I'll just call it iter, right? And the iter is going to assume that I guess we could do parse chunk at, something like that. And when I do parse chunk at, I'm going to say I want you to start at header +1, which is just whatever's right after the header. And I want you to assume that that is the chunk that we're going to start working on. Okay. So again, what I'm doing here is just making a little utility that I hope will be useful in making it easy to read this thing, right? So I'd have something like that. And in fact, you know what? I'll just go ahead and read do the usage code first, like I normally say. So if we do this, something like this, so that'll let us iterate through these guys. And that means that when I do parse chunk at, I also have to do, something like, say, something like this, where I'm going to go ahead and say, whatever the data was where I was starting, we're going to go however big the header says after that, right? And again, I don't know if that's inclusive or not. So in other words, I don't know whether it should be header +1 or just header here plus the header size. That's something that I couldn't quite see in the docs. But we'll be able to figure it out when we actually step through it, and then we'll be fine. All right. So then we've got a little thing here, and I guess now that I look at it, because we only use one of these, I was going to do a little type safety thing here, but we really don't need to, because it turns out that we really don't ever call this in any particular way. So anyway, what we want to do here is just say that get chunk data is something that gives back whatever the contents of the chunk was, right? Oops. Again, with that annoying insert there. So what I want to do is say, if you ask me on an iterator what the chunk data is, also I suppose these should all be inline. They're tiny little, they're really just utilities. They don't do anything. So they should probably be inlined completely. So get chunk data is going to go ahead and return that at pointer plus just the header part, right? So it's going to be whatever's after the header is presumably the actual data that the chunk contains, right? That's the specification. All right. So get type is going to give us back some kind of a uint32 that says what the type is. Now, the wave chunk itself, I don't remember how this actually worked. Let's take a look here. It looks like the wave chunk has an ID and a size. So what we want to do there is we want to return that ID, right? So we want to be able to say that the result here is the iterator chunk ID, right? And then we can return that. So I guess, to be completely honest with you, I don't really know where we left things at the moment in terms of sound playing. We have game output sound. The moment is still being called, and I guess we actually are outputting something here, which is, I guess, this. T sign, we don't actually have. I could make that though. Let's see, game state T sign, game state T sign. Does that ever get incremented? Plus tau 32 of wave period, game state T sign, tau 32. All right, so I guess we would just put this back in, right, for testing purposes. I don't know what else to do at the moment. So I'm going to go ahead and put that in just so we can see if our sound output is still working first with a sine wave before we do anything else. So here's our T sign, and I'll go ahead and run that and see if we have any sound. We do. All right, so that's all good. So if we want to play an actual sound wave now, that's, you know, if we were going to do game output sound for something else, I guess what I could do is just say, well, let's say we've got a loaded sound here called test sound, right? And I'm going to go into to the place where we loaded the sound there, load WAV, and I'm going to say that game state test sound equals that sound. So when we come in here, and was that, so I had that at the beginning, so that was actually loading the sound every frame, and apparently that was fine. That's kind of crazy. Anyway, so I'm going to put that in here when we actually do this. This is just, you know, to test the debug loading. That'll go ahead and load it into test sound. And then what we can do, if we want to, is we can have this game output sound thing actually do something a little more useful, potentially. I don't actually know why I have a separate function called game output sound, but yeah, whatever. So if we actually get rid of this, I'm just going to say that that's not getting called anymore. If I actually just come in here and put this in here, I'm going to go ahead and say we're going to output to the sound buffer like so. And the sample value that we're going to output is just going to come from that debug sound that we loaded, right? So I'm going to say that the game state test sound, what did we call it? Samples, I think. We're going to say that sample 0, that first channel, I'm going to grab the sample index of that and put it into the buffer. Now, of course, we want the sound to continue playing over time, so I need some notion of the global sample index, right? So I want to do something like uint32 sample index, or test sample index, like this. So what I want to do is say, okay, you know, it's actually going to be the game state plus wherever we were in the sound plus the sample index. Then at the end, we'll go ahead and advance that by however many samples we actually retired, like so. And then all I want to do in here is say, oh, you know, I never want you to play more than whatever the sample count was, obviously, right? So whatever its sample count was, only play that many, right? So let's take a look. What did I do there? Game state sample, test sample index, right? Mod test sound dot sample count. Missing. You're right. I am. There we go. Or maybe not. What did I do? Game state. Oh, sample value. That's what I wanted. And so that was actually correct. Sample out. Whoops, did I not copy the thing that actually figures out where we're writing in the buffer? music underscore test. All right, so let's try that. There we go. Okay. So now it'll just kind of play something that's a little more innocuous, and that'll be fine. All right. Okay. So now we can actually go to the Q&A. Oops, I double. All right, so if we're going to do that, we already did part of what we need to do for that, right? We have asset slots for sounds. What we don't have at the moment, and we also have tags for sounds, right? What we don't have at the moment is actually any way to load a sound, right? We don't even have anything like that. And so when we have something like load bitmap work here, we have load bitmap, we basically want to make an exact copy of this conceptually, but instead of doing it with bitmaps, it would do it with audio. So instead of doing the work necessary to load a bitmap out, it would do the work necessary to load a piece of audio out, right? And so what we want here is something that looks basically like exactly the same, something like this, where it does this, but for sounds, right? So here's sounds. Here's the ID value for them. We set the the asset state of them and does exactly the same thing. We then begin a task for it. We get the task out, but instead we would do like a load sound work here, and then we would just fill out exactly the same stuff. Only it would be instead of a bitmap or something like this, it would be something else entirely, right? So yeah, that is what we. We have gotten to the point where we would like to do what I would consider, perhaps even really the only hard memory management problem that we will have in Handmade Hero. Because we talk about memory once in a while on Handmade Hero, but usually it's to point out the fact that you really just don't have to think about it that much. There's a lot of people who think that they can't program without a garbage collected language, or think that it'll slow them down too much, or have all of these sort of preconceived notions about how hard it would be for them if they didn't rely on these sort of abstract notions of memory where it's just kind of amorphous and weird, right? But so far on Handmade Hero, as I hope I've demonstrated, is you really just don't have to think about it that much. There's a couple times that you might think about it a little bit, but on the whole, you can model most things as very simple stacks. You write it once, and you really never have to think about it again. And so that's the case for most of the time, but there's two places in Handmade Hero I think that we might have to think about it. One of them is what we're at right now, and so I wanted to talk about it. And one of the things that's kind of important to remember about this is actually this one in particular is one that also can't really be solved by a garbage collecting language. So this is a problem that you really have to think about no matter how you choose to model your memory, if you care. If you actually care about being able to do some of this stuff correctly, you actually have to think about it whether you're managing memory yourself or not, because it's less about remembering to free stuff or collecting garbage and that sort of stuff, and more about how to make the optimal use of a fixed amount of storage space. It's a caching problem, really. So what I'd like to do today is just talk about this problem. I don't know how much programming we'll do, but what I'd like to do is go to the Blackboard and basically try to give you some of an overview of the problem we're trying to solve, why it's very difficult, ways in which you might just decide not to solve it, which is certainly an option, and then we'll make some decisions or decide kind of what our first stab is going to be like in trying to solve it for Handmade Hero. All right. So here on day 157, let's go ahead and talk about the problem we have, which is asset memory management. Okay. So here's the thing. All of the crazy Java versus C# versus C, memory management, oh my god, pointers, no, it's so hard, I can't program, blah, 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 like, and everyone fights. It's cognitive load, they say, all these other things, right? It's this gigantic nightmare, and you never want to get into those arguments. Just take it from me, if someone starts saying stuff like garbage collection is a cognitive load, just let them take their cognitive load and go load it up, right? Like, it's not even worth arguing with those people, but if you're someone who's really actually legitimately intellectually interested in this topic, here's a good way to think about it, right? So there's a couple things that you care about when you care about memory, right? Number one is how much, right? Right? So there's quantity. And this is just how much memory do you actually need to run? Like what is the actual footprint, right? And we care about this because there are times when that's actually constrained. And no matter how much anyone would like to pretend that that's not true, it rears its ugly head again and again and again and again. We don't have to care about memory because PCs have a lot of memory. Oh, here come consoles and they don't have a lot of memory. Okay, finally consoles get enough memory. Don't worry about memory, it's fine, we've got plenty. And then all of a sudden, phones happen. And now phones have no memory, right? And then when phones get memory, all of a sudden it's going to be something else. It's like, oh, wearables, I got my little wristwatch, and the wristwatch has no memory, right? It's like, it seems like throughout time, no matter what happened, we always run out of memory, and you always have to care how much memory you're using, because no matter when we think we have enough, either what we want to start using in terms of assets gets too big, or the machines suddenly come out that we want to target that are too small, right? So quantity actually is important, and we need to think about that, right? Two is when, right? And when is like, sort of the concept of alloc and free, right? Where do these things happen in the code? Because there's how much memory we need at any given time is one question, but how we track when we need which parts of it is kind of a different thing, right? And so if we think about garbage collection as a thing, right? Garbage collection is and languages that manage memory for you are really entirely about this, right? They're entirely about figuring out when you need the memory. They have nothing to do with this, right? So no matter what you've got for a language, it doesn't help you use less memory if your code is written so that it needs that much memory, right? It doesn't help you at all. So really the only thing that garbage collection helps you do is if you can't figure out how to write your code so that you know when you need memory, garbage collection can help you, because what garbage collection effectively is it's a search over the graph of your program's ownership structure to see what memory is actually in use. And when that ownership structure changes, the graph search will then figure out, oh, there's been a piece that's now been calved off, it is no longer necessary, so I know that it can be freed, right? And so garbage collection is basically replacing you, right? Garbage, in fact, I could even just summarize it. Basically, all garbage collection is garbage collection means it replaces you with search, right? That is what that is. So instead of you having to know when things are alloced and freed, it will search to figure out what those are. And basically all of the research around garbage collection and all of the technology around garbage collection is designed to figure out how to make this less expensive, right? Because if you actually think of it as a real search, it would be impossible, like it would be totally impractical, because running that search every time you did something would just be prohibitively expensive. So what they do instead is, well, okay, can we limit the search space to just things that we know have changed recently? Can we do it only at certain times? Can we overlap it on other threads? Blah, 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 right? And so there's all these sorts of things that try to make this less expensive, right? So the reason I dismiss garbage collection as uninteresting is because, as you've seen so far on Handmade Hero, when is not really a problem for us. Like, we just don't have that problem. We've literally not even come to a single point in Handmade Hero so far where when we even thought about it. We just know we've got some stacks, we put stuff on the stack that's appropriate, and that's it. right? It just doesn't matter. Because we know that the world exists as one thing, and we just run it, and we don't really have to think about it much more than that. We know when something gets destroyed or whatever that it's been freed, so we don't, it's just really, there really isn't anything a garbage collector could do for us. So all we would be doing would be either you are confused about it, or maybe you have some very wacky program where it's just, this is going to be the only way to really know for some. And one place that might happen, let's say, was like some kind of editor with really dense, weird structures in it, and you like delete one of them, and it's hard to tell whether some of the other related, or in a more game context, like maybe we'll see it later on, where we get into a situation where there's like entities that have sub-entities, and when one of those goes away, like should other sub-entities of it go away, or what I'm saying? So that's really the only time where you can start to see like, oh, okay, I get it, like that's, garbage collection, while I'm personally not interested in it because I just implement something myself there, you could at least see where it might be useful. Whereas in Handmade Hero so far, we haven't had anything where it would be useful, right? So it's just kind of a no-op. But eventually maybe we'll get something where it is, and I'll point it out if we do. If we don't, try to imagine that in your head, and that's what that's doing for you. It's preventing you from having to write code that detects what that is, because it's like a generic version of that thing, of the, oh, I deleted an entity, are there any entities which are now irrelevant to the game and should also be deleted? That's like what garbage collection is supposed to solve, the generic version of that, so you don't have to write it yourself, right? So there you go. Okay. So what we have, unfortunately, in the asset memory management thing is this is not really relevant. We don't care about this at all, because when is not at all the issue in terms of when the memory is used. Because what asset memory, if you think about how this works, is, right, we have something that's like, let's just say it's like a bazillion, right, assets. However many there are, we have a huge number of them, right? And then we have some amount of space that we have to run our game in, right? So let's say this is like 3 terabytes, because who knows, it's the world's largest game, right? So, the community gets together and they make 3 terabytes worth of assets for Handmade Hero, and we're trying to run the game with 3 terabytes of assets. But guess what? We only have 4 gigabytes of RAM, right? And so what we need to do is the when for memory is always. There's no time when we didn't want all these assets. We wanted all of them, right? They're all in use. None of them will ever be garbage collected. None of them will ever be garbage. We need all the asset data. It's all there. The problem is we can't fit it all in memory. So what we essentially have is a caching problem, right? We have a problem right here, where the amount of memory that we need is larger than the amount of memory we have. And just to underscore why this is irrelevant, if that wasn't the case, right, if we had 4 gigabytes of assets and 4 gigabytes of RAM for the assets, we're already done. Our asset system already does the exactly maximally efficient thing, which is that at any given time, the assets that it predicts that it needs are getting loaded into the 4 gigabytes end over end over end. You can actually see this. I'll load up the code and show you exactly what I mean so that it's concrete for you and you know exactly which part of the code I'm talking about when I say this. If I go into handmade code, handmade asset, right, then when we do that sort of load asset work stuff, right, you can see in load bitmap, what we do right here is we do a push struct to push the bitmap sort of handle on, and then we do a push size to push on the bitmap bits, right? And that goes into our asset arena. Now, if that asset arena will never fill, so we've got 4 gigabytes asset, 4 gigabyte arena, and they'll fit. If it'll never fill, we're done. Our asset code as written will do exactly the right thing. It will load all the assets into memory eventually. It will load them in the order in which we need them to be loaded, and it will do so in the background so that you don't have to wait for a loading screen. So it's exactly what we want if our asset load is lower than our memory footprint allows us to keep at one time. So the reason this turns into a caching problem is because if we have more memory than would fit in here, right? So it's too much. then what we have is essentially a VM problem. We've got a virtual memory predicting. Garbage collection doesn't help us here because garbage collection doesn't solve this problem, right? This is just inherently a virtual memory problem, and what we want to do is essentially say, well, we always have a handle to all the assets in some sense. None of them are ever garbage. But we only want you to have ones resident that are ones that we believe ourselves to need in the immediate frame or in frames that are coming up within the next second or two, right? But things that are going to be used in 30 minutes, we don't need to have those in memory right now, so you don't need to store them, right? Okay. So, ways we can cheese out on this, right? So what this means, and again to underscore why the garbage collection doesn't help you, and also, in fact, I'll show you why both doesn't help you. So we have, we talked about two things here. I was like, we've been using stacks. Other people say garbage collection, woohoo, right, or whatever. So why did neither of those two solutions work for us? Why don't stacks and or garbage collection work for us, right? Well, the reason is because if we have 4 gigabytes of memory, right, then what we've got in that 4 gigabytes of memory is some grouping of stuff in there, right? We've got asset A, asset B, asset C, asset D, asset E, asset F, or whatever, right? In a garbage collected system, we have handles into these, right? And what we would need to do in order to make room for the new assets to come in is we would have to tell the garbage collector that we no longer need B, right? So we'd need to basically free B, right? So garbage collection doesn't help us because we'd have to explicitly tell it to get rid of that. Otherwise, it would still just pile up. And the same thing is true of the stack. As the stack gets pushed on there, right? A, B, C, D, E, F, right, or whatever, we need to tell it to free one of these guys, right? It would free B, and then it would know to get rid of B, right? In either of these cases, sure, we could then say, well, okay, that's good enough, right? I mean, yes, we have to do free, so maybe it's not garbage collection, but now it's a heap or something, right? Now it's like, well, we still could do it. We could say free B, or we could say free this thing or whatever, right? Not exactly. The reason for that is because when we free something out of the inside of an asset pool like this, or inside of the stack, right, we end up in a situation where it leaves a hole. It leaves a hole in the memory. And in order to put something else in that hole, the thing that going into the hole has to be smaller than it. Something smaller than it's in is that now I've left an even smaller hole that probably nothing could go in, or very few things could go in, right? And this is called fragmentation. Of the memory that you have is small, and then I freed the memory and I loaded something else in, so I had just this part used, but I had already put something in after I free and realloc the 4 gigabytes with these sort of holes in there to an asset because it's in use or whatever, blah 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 blah, right? So fragmentation is a huge problem where you're trying to maximally fill this space that you've got. You constantly run into these problems where you're like, crap, I can't just free one resource and put another resource that's in its place. If they're not the same size, I leave these little fragments, and who knows how long it'll be before I can actually start to do something with those, right? And so again, yeah, garbage collectors don't address this at all. Neither do stacks, but what's underneath could, right? So a garbage collector could be built on top of a memory allocator that does try to address this, right? And similarly, for our usage, we could imagine doing something similar, like building something underneath it, which does handle this, right? So let's talk about that. And that's really what I want to talk about today. How much time we got here? So 35. We're going till 15 after or something like this. So 6:15. So yeah, we got plenty of time. We got 40 minutes. Okay, 40 minutes. Is that right? Yeah, we got 40 minutes. So let's talk about this problem. In a world where all the assets were the same size, we would be very, very happy campers. So if all the assets are the same size, A, B, C, D, E, then when I need to load a new asset, right, I need to load asset F, it is exactly the same size as everything else. So what I can do is I can look and see which of these assets is the oldest, the one that hasn't been used in the most number of frames, let's say. And I can take that, evict it, right, and stick the new one in its place. So we get rid of asset C, if that's the oldest, let's say, and we put asset F in its place. There is no fragmentation. Everything is always used perfectly, because however much space there is, let's say there's 4 gigabytes of space, if every asset is, I don't know, 256 megs or something, then I know I have space for 16 assets. I'm always storing exactly 16 assets. Whenever I get a new asset, I evict the oldest of the 16 and put it in its place, and the memory is always guaranteed to be used maximally and perfectly. No problem, right? And this is why fixed size allocators, right, are really great. Any problem that you can turn into a fixed size allocation problem is really fantastic, because it will allow you to basically do perfect management of the memory, never have any fragmentation. It's very, very simple and straightforward. And we've seen this before. We've done it with a free list. I don't know if you remember when we did free lists, where we just reuse blocks of that size to kind of just like, when we free, we just keep the old ones around and then reuse them again. That's a classic example of a nice fixed size allocator. They're so our problem, we kind of have 2 ways we can go with it, right? What we want to do is we want to handle the solution, we want to handle the situation where these assets are not the same size. So how do we do that? Well, the first thing that we can look at, right, is the fact that we could choose to make this into a fixed size allocation problem, right? That is actually an option that we do have. And the way that we would do that, for example, is let's say you just flat out decided that all sprites are 256 by 256, right? Let's just say you just said that. If that was the case, then all of our bitmaps would be the same size. And at that point, it would be pretty darn easy for us to go ahead and load the bitmaps on top of each other, because when we freed one, we would free exactly the amount of space we would need to load the new one in, right? So that's pretty compelling. The problem with that is that doesn't really necessarily do a good job of representing what we actually want, right? It doesn't make sense for us to force all of our bitmaps to conform to this size because, some of them are larger, some of them are smaller. It would be wasting space or whatever, if we did that. And so the other thing we could do is we could say, well, okay, we could tile things, right? We could make it so that everything was in tiles. So, if we had the hero or something like that, instead of the hero just being one bitmap that was a certain size, we broke it up into ones that were 256 by 256, right? So if you want a 512 by 512 hero or something like this, you break him up into 256 by 256 tiles. It's an option, right? You still have some wastage, right? You still have times when it's going to be too big. Like if the hero was only supposed to be 270 by 283 or whatever, right? Well, you've got a ton of wastage now because you've got, the hero only taking up, maybe that much of your 4 tiles, and there's all this empty space there, right? But there's even stuff that we could do to try to mitigate that, right? And to sort of, one option that we easily could do is say, let's pretend the game is one gigantic sprite sheet, right? And all of the sprites are like packed into the sprite sheet, not by hand, but by an automated process. And then the sprite sheet is just broken up, into 256 by 256 tiles. Then when we say we want to load a sprite, we just have to figure out which set of tiles it needs, virtual texture, and it has some merit, right? It definitely has some merit to it. So I wouldn't necessarily dismiss that out of hand. We could do something like that, right? But there are concerns around this, right? The biggest concern around doing things this way is what you do about MIP mapping, for example, because MIP mapping gets very difficult in schemes like this for reasons that I don't really think we necessarily want to go into in detail here, but there are reasons why you might not do it. Now, with a 2D game, it's possible that we could get away with it, right? In a 2D game, it's totally possible that we could get away with it because in a 2D game, you know what the MIPS are ahead of time. You don't have to do like trilinear, and you don't have to have a lot of angular stuff going on where the MIP level is going to change across a single polygon. So it's actually plausible in a lot of cases to do a scheme like this for a 2D game, I think. So yeah, so I'm just going to put that out there. So that's one thing that we could choose to do. And what that does, just to be clear, is it doesn't quite get you entirely out of the business of having your assets be different sizes. Because even though it now means that the actual pageable asset that you're working with is all the same size. So we have a uniform size for the pageable asset, which is a tile. What it doesn't do is fix the problem with the asset tile list, right? So we still have the case that asset A, if it was a 512 by 512 asset, right, it's got 4 tiles in it. But asset B that was 256 by 256, that only has 1 tile in it, right? So you still have a variable size to your assets. This one requires 4 indices into the tile table, and this one requires 1. But because 256 by 256 by 4, right, the actual size of the sprite data is, well, to put not to put too fine a point on it, right, but 256 times 256 is 64th, k, right? 64k times 4 is 64k more than what it takes to store an index, right? And so what you can choose to do is just not page the tile set, right? So the thing that stores the asset tile list could just be loaded in memory at startup. It's probably pretty small, like, okay, so it's a 10 megabyte thing or something like this. You just load that in once and you're done. And then you're just paging in the tiles as necessary, right? So that's one thing we could do. And as I'm saying it to myself, I am kind of wondering if that's not the best solution, right? Like, I don't know if that's a smarter solution to the problem than what I was going to propose here, but we'll see. I'll keep going. So our other option, right, is to do a regular allocator, right? So if we do sort of, for lack of a better term, a variable allocator, one that can allocate things of variable sizes, what we can do is say, okay, we've got our memory here, right? So we've got our 4 gigabytes. And what we would do is we would go in here, we would allocate a chunk of memory for a resource, an asset A, right? And then we would go in here and, allocate one B, and then go in here and allocate one C, right? If later on we then deallocate B, let's say, right? So B goes away, and we put something else in it. So in comes a new asset, D. We've lost the ability to kind of use this space because it's like maybe too tiny now to really load much of an asset in there. So this space has become fragmented. Then what we can do, we have really 2 choices actually. One thing we can do is, because our asset system is already indirected, because the asset table itself points into these things and people always reference assets through the asset table, we can then start to do some kind of compaction. Like, we could move C up to close in that space, right? We have the ability to basically do defragmentation. So that's one thing. We can actually move stuff around in here. But the other thing that we could do too is, as stuff gets freed, we can do the standard stuff that you do in a variable allocator, which is we would actually condense on free. So when you start to free stuff, when you get, you get this little space in here, if C then were to get freed, we would record the fact D-sized space to be used. We would now know that we have space that's the, actually a B minus D plus C sized space to use, which is a bunch more open memory, right? So probably the thing that I say that we might as well just go ahead and do, because it's possibly a good exercise to sort of go through the steps of making a variable allocator so you can see how one works, because at the end of the day, that is what malloc and free, what new and delete, what these things do. And it's also, if you're in a garbage collected language, it's what the thing underneath the hood in a garbage collector has to do too. Because remember, underneath the garbage collection layer, you still have to have something that can do random size free alloc and free, right? Because at the lower level, the garbage collector still needs to be able to reuse memory efficiently. Otherwise, it's going to be a really bad garbage collector, right? So yeah. I kind of felt like that was the right thing to do for our asset system, even though it, maybe it's not the smartest way to do. If the thing you go through, when you call load bitmap, it goes ahead and allocates stuff. But what we would then do is we would put sort of a cap on its allocation limit, on its allocation size. So when it gets up to some number of gigabytes, right, however much we set aside for asset storage, when it gets up to 1 gigabyte or whatever we said, it will then have to free enough other stuff to basically give it space, if you will, sort of give it space to ensure that it's never going to use over that 1 gigabyte amount, right? So that's it. That's all we're talking about. Nothing more complicated than that. It's pretty straightforward, really. There's nothing particularly conceptually difficult about what's going on. It's just a very finicky kind of a thing because it's about placing things and looking through structures to see where, if there's free space and whether you can fit something in, or would it be smarter to put it somewhere else. And, it's just kind of this nasty, it's that kind of a sort of nasty, finicky code. And so, while there's nothing particularly tricky about the high concept, when you actually start getting down to how do I do a good job at this, it can be kind of tortured and weird, right? And to some degree, it's sort of a black art, I believe, too. I don't tend to write much code that goes through variable allocators, so I'm actually not the best person to say what the state of the art is in terms of variable length allocators, but my experience with them in the past has been roughly that it's sort of a black art sort of a thing where it's like, yeah, there's certain allocations schemes seem to be pretty good at the kinds of stuff that people do with allocation, right? And so, you'll see people saying, oh, I used dlmalloc or whatever, and it was good for this workload. And it's just like, these are just like arbitrary schemes that people kind of tune to be good at arbitrary workloads that they were testing, and had good performance in terms of not taking too long to find out where things should go, and being able to use a reasonable amount of memory without too much wastage, right? Without leaving lots of empty space, and all these sorts of other things, right? All right, so we've got about 24 minutes, something like that, 24 minutes left. Go into this system. So when we say memory index size here, when we allocate, for those of you who missed it on Thursday and Friday, we added a particle system. I said, what should we do for a fun diversion? And particle system was on the list. So we added this, and you can't tell me that's not hilarious. That is just hilarious. All right. So yeah. Okay. So here's what we need to start thinking about. Let's start this process here. Let's recover from the humor of seeing a bunch of weird little tiny heads spew out of our hero's abdomen. So we've got the asset system, and the asset system itself has this memory arena, and so it's allocating things on this memory arena. And what we want to be able to do is we want to be able to have some kind of an opinion about when we need to free memory and like how much headroom we need there, right? So let's take care of a few really basic things first that we kind of need to address, right? So one thing that I was thinking about is for our asset slots, I wanted to think about whether we wanted to expand the asset slot set to, how much memory would it take to expand the asset slot set to just have the data in it itself. And so what I'm going to do here is I'm going to go in and I'm going to take a look at what the loaded bitmap stuff does. And I'll show you what I'm talking about here. So if you take a look at the loaded bitmap stuff, and you can ignore the 5-minute warning because, like I said, we got 15 extra minutes on the clock today, so we've got 20 minutes. It was a long question day today at startup. Yeah, so if you take a look here, if we just take a quick look at what we're looking at in terms of loaded bitmap, you can see there that's what the loaded bitmap looks like, what the loaded bitmap code looks like. We need to store width over height. We need to store the alignment percentages for where the bitmap should be centered. We need to store the width and the height of the actual bitmap itself, and we need to store the pitch. Those are the things that we needed to store. Now, my assumption, and I could be very wrong, and that from now on, I'm sorry, from the width, and then so we could get rid of that, right? So that could go away. So let's try that first. And again, what I'm trying to do here, just to say it again, what we have in our game is we have this asset slot, and we have, as if they were packed, which is they have a 32-bit state variable, which does not in any way need to actually be 32 bits. If you actually look at how big it is, that's totally not necessary, right? And then they've got pointers out to whatever the actual data is that would be there, right? And so they're 12 bytes or something like that. What I'm wondering is, could we just get rid of loaded bitmap? I'm sorry, could we get rid of the pointers and actually put loaded bitmap and loaded sound directly into the asset slot so that it's just always there? Why do I want to do that? I want to do that because it means that assets are only the size that they actually are from then on. So we don't have to constantly think about allocating a loaded bitmap structure to point to and then have that point to the memory, right? I'm just removing a little bit of indirection there. Because what you see happen, if we actually go to load bitmap or something like that, right, is you see that first we do a push struct for loaded bitmap into the arena, and then we do a push size for the memory that we actually need. So I wanted to get it down to just the memory so we know that assets take the size that they are, whatever their size is. Is what they take, right? So yeah, so I just want to condense these structures down and then see if I can put them in there. So let's think about that pitch, do we actually need to store that? So let's go ahead and see if we can get rid of it, right? So what I'd like to do is just replace that with a thing that's like get pitch, right? Some function that we just call. So every time the pitch is talked about, we actually just do like a get pitch call, right? Something like this. And so I guess, now that I look at it too, I can already see what the problem's going to be. So I wonder if we want to do one more step before we do this, which is that when we're actually writing to stuff, those are technically loaded bitmaps as well, because we don't distinguish between the two of those things. So the actual problem is going to be how we handle buffers we write to, if that makes sense. And so I feel like what we would almost want to do is do something like struct like a writable bitmap, right? And that thing has an extra pitch on it that the other ones don't have. Does that make sense? I may try to do that. Let's do something simpler first, though, since I can see that that's going to be a little bit of a problem. So we'll try that first. We'll try something else first. So first of all, width and height right now can be 4 billion by 4 billion. So there's really no, well, 2 billion, they're signed. So there's really no need for that, right? That is not at all necessary, I don't feel like. So one thing we could also do here is we could choose to store this in a much smaller way. Now, 8 bits isn't going to cut it because 256 by 256 is too small, but 16 bits would certainly be fine, right? 64,000 by 64,000 is bigger than any bitmap we're going to have in Handmade Hero because our screen is not even that big. So that would be kind of overkill. In fact, our screen would at most be like 4K, so we'd be talking about 64 by 4. We'd be talking about a sprite that was 16 screens wide. Not going to happen, right? So we could change these guys to 16-bit, and we wouldn't miss it, right? That would be totally fine, right? And so that gets us down to 2, 3, 4, 5, and then the pointer, 6, 7, right? And so we could also, of course, change the pitch to also be one of those. And then I'm not sure that we could really do much else. We need these guys to be float, right? So yeah, we really would want to get rid of the pitch because that would leave us dangling at 16, which we don't really want to do. So that would be 4. What we'd really want to do is get it to this, because then what we'd have is essentially 2 floats, 1 float, 2 s16. So it would be like 4 4-byte things or 16 bytes, and then the pointer. Right? That would, I think, be probably what we would want, right? So that'd be good. And if we were down to that, right? If we were down to that, that's basically just talking about that's talking about 16 bytes extra per asset. And we could also do a little snuggling there. We could snuggle that up a bit. Because if you think about what happens with this asset slot, we have this asset state in there. That asset state could probably be stuffed into here somehow in a relatively, in a relatively sort of cozy fashion, if you will, right? In fact, if I did it like this, now the asset state could easily just be a U16, and off you go, right? Of course, the only problem is we do atomic writes to that guy. Yeah, not sure. We'll find out in a second. Let's find out. Okay. So here we go. Let's see. At least I think we do atomic writes to that guy. I could be wrong. Yeah, we do atomic writes to that guy, right? So that's no good. So that's no good. So that guy has to stay as a U32, basically. We'll have to play around with that a little bit, because we could do stuff to make that not be an issue. All right, so let's go in here. All of these, I think we just want to do, oops. We want to just do a safe truncation. I don't know if we've got a safe truncation there. Let's actually take a look and see if we do. Code, handmade intrinsics, truncate, handmade platform, truncate. Here we go. So what we want to do is something here where we can safely truncate something from a 32, some kind of a 32-byte value, a 32-bit value, down to a 16-byte value, just so we can ensure that, it's not going to be, that we didn't accidentally truncate something that we actually wanted, right? So we want to do something like, we want, what is it, 65536 divided by 2. We want 32768. We want to make sure that it's greater than 32768 and less than 32767, because we know that will be able to be stored in a 16-bit integer, so we can go ahead then and cast it down, right? Although I guess, now I think about it, if we do a safe truncate, if we did something like safe truncate to uint16, then really what we want to do is something more like this. We want it to be less than 65536, or 5, and greater than 0, because we want to truncate it in that way, right? So that's a little more, that's more what we were trying to do there. Okay, so in this case, that should be fine. We'll keep that result there. And then we can just go ahead and do these safe truncations. So there we go, right? And yeah, and you can see that that pitch is very easy to compute in here. So we know that we can do it for everything except for bitmaps, basically. All right, so we're going to just know object file generated, initializing conversion from uint32 to uint16. That is just a typo. Okay. So these guys, again, are also safe truncations, like so. And one more time. Okay. So that should just be fine. And of course, we should still crash whenever, well, not crash, but we should assert that as soon as I use enough bitmaps. Okay. And so inside asset here, let's go ahead and just finish this off. So for loaded sound, the same thing would be true, right? I'm going to go ahead and say that the sample count and the channel count could be shrunk quite a bit. And what I would assume is the sample count, you know, does it really need to be a 32-bit value? Could it be a 24-bit value? So what I might say to do here is, could we go ahead and pack these so that basically we have, you know, sample count is 24 and channel count, you know, is it could be even less, right? The channel count could be 4 bits and the sample count could be 28 bits or something like that, right? So if we packed those guys together, again, that would keep it even smaller. And so then it would be basically the same size as the loaded bitmaps as well, right? Although now that I think about it, it might be that the loaded bitmap is still a little bit bigger. Let me take a look at that. So in render group, so loaded bitmap, it's got one pointer. Then these two guys would then count for another pointer. So then you've got the R32, which would count for it. So yeah, so basically the loaded bitmap's always a little bit bigger, so I suppose we don't really have to do that one. Because since they're both stored in a union, right, unless I could get them both down to a smaller size, it wouldn't really matter, right? So I'll just put to do in here to do, if the loaded, and also we don't even need 2 pointers, so the loaded sound, this could be shrunk to 12 bytes if the loaded bitmap ever got down that small, right? So yeah, that's all I wanted to just mention there. We don't need to go totally crazy with it, but it's something we could probably do a little bit more of. And you know what, I'll put one into this too, where I'm like, just to do get rid of pitch. And we'll try that in a second, potentially. All right, so what I want to do now is I want to just make these guys actually stored, right? So instead of being pointers, they're just actually going to be stored in there. And we'll make the asset state be the only thing that actually determines whether you can use them or not, which I think we already did. Like, we already did this check, right, to make sure that the thing was loaded. So I think we're totally fine on that. So basically all we're doing here is making it so that it's going to use it out of there directly. And we no longer have to do a push struct on these guys. What we can do instead is just take whatever was in that slot and use what was in the slot, right? So yeah, so we can go ahead and take this. In fact, we can probably do this at the top here, where we just kind of go like asset slot equals whatever the slot is, like so. I guess we don't have to do that until we actually use this thing. And then in here, we can just, you know what, we could probably even just do it like this, because it's not invalid to just do the computation. We're never going to access it unless it actually is valid. We can just come in here and say, oh, okay, you know, instead of actually doing this, we can just do it off the slot pointer like so, right? So now, when we want to use this, oh, and I guess I could do this here, slot unloaded. So now, when we come in here, I can just say that the bitmap is just the slot bitmap, and you don't actually have to do anything, right? And that means that we don't use up any additional memory, and all this stuff should just work fine, right? So I can go ahead and compile that. I think that's really all we need to do. And this doesn't actually need to happen at all, right? Then in here, the same is true. We don't actually need to do that anymore, but we do need to actually pull out that slot. So here it is. Then we can, you know, in here, take that, use that slot. Now it's already been kind of pre-addressed for us. And in here, we can avoid ever doing that, that allocation for the sound. So I'm just going to take the address of the sound that's already there for us to fill in and use it, right? So there we go. And while we're doing this, I think I might go ahead and turn the music back on, just so I can hear that it's still loading properly in case we make a false move that makes it so that our music stops playing. That would just be a good thing to keep in mind. So there we go. Aha! And of course, just loading the music was enough to blow out our amount of space that we said we could use. Let's try and change it to 3 megabytes. So now, just by virtue of playing the music, or creating the guy, we blow out the arena, right? So that's good. Okay. So all that's nice. And now what we need to know is we need to have some way of now determining ahead of time when we are going to hit our load limit, right? And this is actually trickier than you might think. The reason this is trickier than you might think, and the reason that we're going to have to probably introduce something somewhat fancy, and you know, when I say fancy, it's not that fancy, but and I should probably, I don't know if I should end now. We need to have some kind of a situation where when we are full and we have something that we want to put in here, right? We're saying we got to load an asset and it's going to take a megabyte, right? But we don't have a megabyte of space. We then need to be able to start freeing stuff to fit 1 megabyte's worth of space. Well, we can't actually free anything at the time when you call this. Why? Well, let's see when it gets called. And those of you who are sharp, who are watching right now, you should know what I'm going to say. You should be able to figure it out. So I'll give you a little couple seconds. Where is this called? Where are we calling load sound, for example? Right? Well, actually, you know what? Load sound is probably not the best example because we don't load hardly any sounds. So let's do load bitmap instead. Okay. So where are we calling load bitmap, right? Well, we're calling load bitmap inside push bitmap, right? And game update and render is where that gets called. Now the problem is, on this frame, we've already called push bitmap a bunch of times. And what happens when we actually call push bitmap is if the bitmap exists, we use it. How do we use it? We put it on a list of things that the renderer will go and use. So, if during this load bitmap call, we were to evict an existing bitmap, we would run the risk of evicting a bitmap that is currently being used, right? So what we would much rather do, you know, because we could try to go the route of introducing locking code to preventing that from happening, right? But rather than doing that, what I'd rather do is say, let's introduce a controlled time when bitmaps are actually marked as freed, so that we don't ever free them in the middle of things, right? And so there's two ways we can do that. One is that when we call load bitmap, we can put them onto a list of things to be loaded later. The other is that we can kick off the tasks immediately at that time using space we've pre-freed. Okay? Time to be loaded things, right? And so there's two ways we can do that. One is that when let's introduce a controlled time when bitmaps are actually marked as freed, so that we don't ever free them in the middle of things, right? And so there's two ways we can do that. One is that when we call load bitmap, we can put them onto a list of things to be loaded later. The other is that we can kick off the tasks immediately at that time using space we've pre-freed. Okay? I'm going to say those two again on the blackboard. We can either keep some amount of free space around in here, right? So we keep, you know, out of our 4 gigabytes, we keep, you know, 16 megs free. So every frame, we can kick off tasks that will write to the 16 megabytes, and at the end of the frame, we will free back up to 16 megabytes. So if we used up some portion of the 16 megabyte of free space we've done, we'll free a bunch of stuff that gets us back to 16 total megs free, something like that. So we always have places to kick off our new tasks to write into without having to evict things. We can do that. Or what we can do is when we do load bitmap calls, we actually defer them to the end of the frame. So when somebody calls load bitmap, we don't kick off the task. We just write in all of the bitmaps we wanted to load, A, B, C, D, E, F, G, whatever. And then at the end of the frame, we say kickoff. And it goes through and it kicks off all of these to new tasks. Right? You can do either of those two things. I would lean towards probably doing the free space one, because I'd rather kick off the load immediately so that we have the rest of that frame's render time to get the stuff that we're missing for the next frame on disk, you know? So I don't know, like, because missing, yeah, I don't know. There's a lot of ways we could make that trade-off. On the other hand, we always probably want to be pre-caching anyway, so this may actually be fine. I'm not sure. But either way, I'd like to go to the Q&A. Because is there any performance reason to not use malloc and free? You mean like if we didn't want to? Okay, I think I know what you're asking. So you're saying if I didn't want to show you how to write one of these, could we just call malloc and free here? And the answer is yes. In fact, you could even do that probably even if you didn't want to use the C runtime library. You could just call the platforms malloc and free, which is like in Windows like heap alloc and heap free, because we're making so few allocations. You know, we're going to make like 16 allocations a frame or something like that for these asset movements or something. At that point, it doesn't have to be super efficient. So yeah, if we didn't want to look at this problem in a little more detail, you probably could just call whatever. It doesn't even matter what. New and delete, malloc and free, heap alloc, heap free. I don't know you want to call virtual alloc, because that's a little heavyweight. But certainly anything else would probably be fine. Are there technical... Dual 1000, can you talk a bit more about what new and delete actually does and when to use them? Sure. So we don't need new and delete on Handmade Hero because we don't use any kinds of C++ features that need them, that need to use them. But basically what happens is you can think about there being sort of two steps to constructing a... you can think about two steps to using memory, right? There's like getting the memory. Two, there's initializing the memory. And then we might as well, like those are the two steps, but we could also throw in step 3 if we wanted to, which is freeing the memory. Right? Or I should say this, you know what, if we're going to throw that in, we might as well do 4 steps. 3, deinitializing the memory. And 4, freeing the memory. Right? And so the way to think about the things that you're asking about, new and delete, right, is essentially, if you look at this process, this is malloc, right? These two together are new. This here is free, and these two together are delete. So basically what C++ tried to do is it tried to formalize steps 2 and 3, whereas C only really formalized steps 1 and 4. Okay? So this is C, this is C++. To make these a little more concrete, let's suppose that I have something here, struct foo. It has an int bar in it. Okay? And so if I want to make one of these that's not on the stack, that is going to be dynamically allocated from a heap, the C runtime library provides you with steps 1 and 4, which is malloc and free. And what those do is they go to the heap and they reserve something of this size and they return it to you. So when you say foo star A equals malloc, right, size of foo, you are asking to do step 1, which is to reserve a place in the computer's memory for a foo, right? And you'd have to cast it here in C++, but in C you wouldn't cast it because the cast is implicit from void. So if it was C, it would be this, right? But the memory you got back is just garbage. It just has whatever is in there, right? It's not, this step 2 was not done for you. And then later, right, you can imagine calling free on A, which is saying I no longer need the memory that you got here, so put it back into the heap. Put it back, like let it be known that this part of memory doesn't have to be reserved anymore. That's step 4, okay? And that's free. So that's what C looks like. And so when you wrote C code, you did this, then you did whatever you wanted to do to initialize the object, like A bar equals 5. Right? There's the initialization. I'm initializing bar to 5. I use it, and then later, if I have some deinitialization to do, I do it. In this case, I don't have any, but you could imagine something more complicated there. In fact, I guess, you know what? Let me help illustrate this a little bit better by saying instead of int bar, let's say it's file star bar. Right? So there's actually another thing inside it. So at initialization time, I want to do bar equals fopen some file. When I'm done with it, right, I then need to close it. So I need an fclose here, and I need to fclose a bar before freeing the memory, right? So again, those are the steps 2 and 3, right? Here's step 1, here's step 2, here's step 3, here's step 4. And so what new and delete try to do in C++ is standardize on this step as a couple. So instead of 1, 2, 3, and 4 being things where 1 and 4 were facilitated by the C runtime library and 2 and 3 were entirely up to you, C++ makes it so that actually those things can be bound together. So if we expand this class to have a constructor, foo, right, and a destructor, foo, right? And I'm calling it a struct, but remember, struct and class there's no difference between these two things in C. They're exactly the same. The only difference is whether things are declared private or public by default. That's it. So if you stuck a public at the top of this thing, there'd be no difference between calling a class and a struct. So, you know, don't let that confuse you. It was a meaningless keyword. It should never have been introduced. It doesn't actually mean anything. It's just a struct. The only thing that we have in C and C++ are structs. And so class was just, you know, someone's little mental, you know, Bjorn Stroustrup had a, you know, an unhealthy attraction to Simulator or something. Okay. So we introduced these constructors and destructors, and what they are designed to do is move the understanding of what steps 2 and 3 are into C++ proper, rather than just as something the programmer does. So what we do is inside these constructors, right, here's foo's constructor. Inside the constructor, we actually do, you know, bar equals fopen, right? And inside the destructor for foo, we actually do the fclose, okay? Right? So that's what's actually happening in the case of doing the C++ way. So steps 2 and 3 move into the class, right? They move in. The responsibility for that is no longer in the outside, it's on the inside of the struct, right? And so the reason that C++ had to introduce new and delete was because now you needed a way of saying, I want to do a malloc followed by the initialization. I wanted to do step 1 and step 2, and that is what new means. And similarly, to be symmetric, they needed to introduce a way to say, I want to do step 3 and step 4, and that is what delete means, right? So the time when you have to use new and delete is really very simple. Did you want the compiler to call the constructor? Did you want the compiler to call the destructor? Or didn't you? That's it. Now, it's worth noting that sometimes you really don't have a choice. in this struct that I have here, it would be trivial for you to malloc it and just not, you don't have to call new. Even if it's got a constructor in it, if you didn't want the constructor to run, you could just call malloc, right? Doesn't matter. But suppose you were to introduce a virtual function. Heaven help you. First, you would get fired from my team, but then second, what would happen is inside this, this struct, foo, the compiler would silently introduce a pointer to what's called a vtable, which is a dispatch table that is how it actually implements virtual functions, right? Now you have no way of initializing that virtual table yourself because you don't even know where that, you don't know anything about that. That's a compiler detail, right? And so one of the things new also does is it initializes any hidden information that you did not put there but that the compiler did. And so if you start using compiler features, C++ features, that the compiler needs to augment the structure of the class with and which have important initialization that has to happen, you must call new even if you don't care about the compiler calling your constructor, because the compiler essentially has a constructor that has to get called, and it is the initialization of that vtable. Okay? So yeah, hopefully that gives you some perspective on what new and delete are and when you have to call them. The reason we don't need to call them in handmade hero is because I find them to be completely superfluous and irrelevant, because if I wanted a function that both malloced memory and initialized my thing, I just write the function. I just write a function called alloc and init, and I pass the print. Like, new and delete are literally two of the worst ideas I've ever seen. I have no idea why they were written that way. They don't make any sense to me at all. They're really, really, really stupid, right? The correct way to have added them to the language, if you wanted to get the features that you were going to get there, I think would have been to just have a way of doing a stack call. So saying like the thing that this thing returns is a stack call, is on the stack, you know, move semantics basically, as they call them nowadays, probably would have been the thing to implement, because then you wouldn't ever care about these at all. But yeah. So I never use these because they're literally worthless in my opinion. I don't think they ever have a point. But like I said, if you ever start doing things like virtual function calls, you don't have a choice. You're going to have to do them. Now, mind you, you know, and this kind of gets into, you know, C++ programming, which I don't care about. But like I said, you know, as much as I bag on other languages like Java and C++ or whatever on the stream, that's just because I don't like them, right? But if you like them, you should use them, right? You know, there's people should program in the language that they want to use. So if you are someone who does like C++ and you're programming in C++, again, keep in mind, you do have other options here. There's a thing called a placement new, right? Which is a way of telling the compiler to generate the code that it needs to generate to initialize an object without allocating the memory, right? So if you want to just do step 2, or just do step 3, you can't actually do those. And so if you weren't aware of that, go read about that. That's something that is pretty important to be able to do if you want to do sort of advanced memory management stuff in C. In C++, it's relevant. Could you briefly comment on how viable it would be? Soysauce the Kid. What is the difference between megatexture and a texture atlas? So it depends. A texture atlas is basically the same thing. Megatexture, when I say that it's, megatexture involves other things. It's part of like how the query works, and it's how you do the texture coordinates into it. So they're two different flavors of a similar thing. Megatexture includes the 3D pieces of it. But if you know what a texture atlas is, that's basically what I was talking about. Do you object to the use of explicit vtables like you would have to use in C? No. I'm actually fine with explicit vtables. In fact, what I wish C++ had done is, instead of making vtables an implicit thing, is I wish that what C++ had been about when they decided to introduce those concepts was actually giving you the tools to write code about vtables conveniently. That would have been useful. What they did was not useful. Implicit vtables are almost never useful. But if they had given you good tools for making your own vtables, like, for example, what John Blow is doing in JAI, that would have been very useful. So let's see. The CISIC. What about resource acquisition is initialization? Resource acquisition, so he said RAII. That stands for resource acquisition is initialization. For those of you who don't know what that is, what that basically... I don't really even know if I want to explain it. It's a modern programming trend that basically says, if you are conceptualizing things in terms of object, because it doesn't really make any sense, it doesn't actually have a meaning outside of object-oriented programming to some degree. Because without the notion of some unit of data, it's hard to describe what it would even mean, right? But thinking about it in those terms, right? If you have an object, then the idea is that the object should be considered initialized once it has acquired its resources, right? Meaning I should not have the ability for objects to exist in partially initialized states where they have acquired some but not all of their resources, or something along those lines, right? So the classic example of resource acquisition is initialization is just saying, like, this is a pretty stupid example, but if I had an object, don't make an object that has 2 file pointers in it, right? Because when I go to initialize this object, there's no way for me to actually do a single initialization step that will make these both valid. So it's entirely possible that I got one of them and not the other one, right? It's not really a good example because you could still, at that point, just throw the exception there. And I'm trying to think of what the best example would be for someone who's never looked at this scheme before. I guess I can still describe it in terms of that. It's what I just said, which is that if I did want to have an object that had 2 file pointers, it has to only come into existence when those are both valid, right? And so this is where you get into exception handling and all those other sorts of things. So what it's trying to say is like, okay, when I define this object, right, and I say I've got struct foo, okay, and I've got my foo constructor here, and then I've got these 2 file stars, right? I've got file star A and file star B, or whatever, right? In this constructor, the idea behind resource acquisition is initialization is inside the constructor, I need to get both A and B. And if for some reason I don't get them, right? Generally, the reason that people care about this and the reason why they fallaciously think it's a good idea is because the destructor for my thing should be able to do the cleanup properly, right? And so if I make it through the constructor for the object, then I know that my destructor will clean it up. If I don't make it through, then there shouldn't have to be cleanup. Because if there did have to be cleanup, no one's going to be able to do it because the destructor won't run, right? Because if I did A and I try to F open the A and it doesn't work, if I threw an exception here, right, I'm fine. If I do A and it works and I do B and it doesn't work and I throw an exception here, now I'm messed up because this file handle leaked, right? So the idea is if you only acquire one resource and you only free one resource in your objects, right? Then you kind of know that you can always rely on the destructor to free the thing that you allocated in the first place, right? And so the way that they, sort of advocate programming with resource acquisition is initialization, is making it so that all of your code is basically constructed in this fashion, where if there was a need for multiple things to happen, those are actually separate objects, right? So the way they would probably advocate that you did this was to say that, okay, instead of having an object that's got two file pointers, what I do instead is I make a file object, right? And a file object is just one file. And then the object that I was making over here is going to be two file objects, right? It's going to be file object A and file object B. And that way, when I go into my constructor and I've got A, B, D, right, they get initialized up here in the mem initializer list. And I'm sorry for people who don't know C++. I don't want to explain it because it's all stupid and a waste of time. But one of them fails, it will throw an exception, which will unwind that initialization and call all the destructor code, which will clean them up one at a time, however many of them actually got initialized, right? So that's resource acquisition is initialization. There's more to it. Like, I mean, that's not a complete explanation of kind of how it works, but just for people who literally don't know anything about it, it's trying to say that the acquisition of something that needs to be, or you can make it even broader. The notion of a resource is just something that has to have shut down, right? As soon as you have gotten something that needs to be shut down, that is the end of your work, right? That is, you have now initialized up, and the freeing, the part where you will free is going to take care of the symmetric operation of freeing that, so that you know that you're not ending up with a lot of things that some of them might be initialized, some of them might not, and how do I clean that up, right? So I don't like this programming model at all. It's really just kind of dumb. I don't really know why people like it. I think it's probably for people who aren't super versed in actually like production code or something. People who kind of think about code more theoretically, maybe. But the reason that it's not very good is because you basically obfuscate the part of the system that was actually the problem in the first place, right? So the problem with the code that they were trying to solve, because with resource, the only reason you care about resource acquisition as initialization is if something goes wrong, right? Because if nothing goes wrong, then it doesn't matter how many things you actually initialized, right? Because you could initialize 50 things and then shut down 50 things, and it wouldn't matter, right? So the reason to break things up into things that do a single acquisition and then a single shutdown is so you can handle an error, right? If you have an error, then you know that you were gonna unwind or whatever, right? The problem is error handling is usually more complicated than this, right? What usually you want to do in an error handling situation is actually look at what the error actually was and take corrective action. And these kinds of systems are fantastically brittle because the only thing they can do is unwind. But unwinding may not be what you wanted, right? And so, yeah, the sort of inexorable binding of this to like a rote series of steps that have to be done symmetrically just ruins all of the flexibility that you had in A, handling errors, and B, handling shutdown, right? Because now you don't know the difference between shutting down in a normal scenario and shutting down in an error scenario. They both have to do the same thing, essentially, right? Because all of your stuff was written in this way where you have these little guys who just do alloc free or whatever, right? And there's no way to get like more information into them because you've constructed them in this way that, you know, you've got these guys with hundreds of little tiny objects in them that all do these sort of symmetric operations. And now you don't have the option of doing them as a batch, because the whole point of resource acquisition and initialization is that they were done individually, right? The trivial example is I want to have the choice of using this thing where I've allocated a block of memory where they all use versus one where, you know, it's just a narrow piece of memory, right? Well, if these people don't know, if they're all written to like do their malloc and free, well, now it's like impossible for me to do an asymmetric version where I, you know, allocated them in sort of this block or whatever, right? It encourages you to write this really stupid code, which always does exactly the same thing, regardless of what the situation actually wanted you to do. And that's true for the error handling part and for the resource acquisition part, which is what this kind of is all about. So I really don't recommend resource acquisition as initialization. I don't use it myself, and I strongly recommend against it. But that's what it is. It's sort of this notion of keeping those things tightly coupled symmetrically. We finished up some general purpose allocation stuff last week. It took a lot less time than I thought it was going to take, even to just do the rudimentary one. And doing an optimized one really has to wait until we put a lot more pressure on the asset system and can even see, you know, where or if it falls down. So we were kind of like, all right, I guess that was it for the general purpose allocator. It just kind of happened, and that was it. So what I wanted to do is move on probably to the next thing on our list, really, and that, you know, is going to be debug code, I think. It's the most logical thing to do. We're getting towards the point in our engine dev here where we want to start locking things down, cleaning them up, and you know, just doing sort of a general thoroughness pass. We've got some bugs and things that we know we have to fix later, you know, things that are not at the level of quality that we want them to be, that we made note of. And so what we want to do is kind of move towards a place where we can be happy with the basic engine layer that we have put in place so that we can move on to working on the game and being confident that all the services that we made will be reliable and we won't have to constantly be debugging them or fussing with them. And we'll only have to actually do new engine work driven by gameplay things that we want, rather than it being some kind of a maintenance headache for us, right? And so what I thought we'd do today is probably start down the road towards fonts, because in order to do much in the way of debug code, you know, we kind of need to be able to display text on the screen because we're going to want to print out, you know, values and just, you know, assorted things that we're gonna want displayed are going to require some kind of font work. So I thought that's what we do today. So I'll talk a little bit about fonts and on the Blackboard, and then we'll do some code. Today is day 162, so if you'd like to follow along at home and you are someone who has pre-ordered the game on handmadehero.org, you want to unpack day 161's source code so that you will be at the same state I am, and that way you can... So I believe, like I said, I don't think we left anything dangling really, other than saying that we probably should optimize the general purpose allocator once we have some workloads, but that's a little bit further down the line. So I'm going to go ahead and just double check that everything was fine, but I'm pretty sure that it was. So yeah, if I go here, we're still all totally correct. Nothing bizarre happening. We don't have asset pre-caching in there yet, so we still have blinking when things first load, but that's about it. And the pre-caching is really just something that's more about us eventually deciding how those calls are going to get issued, because the asset system actually already supports it as well. So I think everything's pretty good there, and so I think what I'd like to do is start to figure out how we can do some better debug overlaying, right? Some stuff that we can put on the screen now to kind of give us a little bit more ability to have insight into what our code is doing. A lot of times people ask on the stream in the Q&A, they'll say stuff like, how do you feel about test-driven development? And just one of the things that's often true about game code is that the hard things to debug are often not really super possible to tackle with test-driven development. Test-driven development really only tackles the easy problems in game development, ones that really just don't super need to be worried about all that much because they won't be accounting for the majority of your dev time in a lot of cases. And so what is actually more important in game development than test-driven development usually is like visualization-oriented development, however you might say that, which is to say that as your game kind of goes through more and more, goes up in levels of complexity, simply looking at the end results is oftentimes not sufficient to know whether things are really working or not. Because there can be a lot of bugs lurking in the code that are very complicated and would be difficult to ever diagnose with a test or simply by inspection or simply by looking at the end results. And so what we tend to do a lot of times is we tend to write visualizations like HUDs, overlays, and stuff that try to show us a lot of heartbeat information to see what the game is actually doing so that we can use our intuition to detect when patterns look like they might be wrong. So that we can investigate further and get some of those harder, more subtle bugs that are very difficult to find any other way. And so that is one of the main reasons we're going to need fonts. This game, I don't know that the game itself will be all that heavy in terms of printing text out, but I think for our visualization we will want it. And sooner rather than later. And so I'd like to talk a little bit about how fonts work in general and then how we can implement fonts in our game. So here we go. Here's day 162, and we'll say fonts, but sometimes I like to call it fonts with a CE at the end. I don't know why. I feel like that's just kind of fun to say, fonts. It sounds the same, but it looks kind of interesting and cooler. So anyway, day 162 fonts. What are we talking about when we talk about fonts? What is incorporated in a font system, right? And I'll start from the very basics for people who don't know any typography or anything, and we'll kind of work our way up to so that no matter where you are on the spectrum of knowing about fonts, we will bring you up to speed. Okay, so obviously we kind of all know, just no matter who you are, if you've ever worked on a computer, you have a passing familiarity that a font is something that kind of describes the way text looks on the screen, right? And you've probably seen, files, TTF files, which are like true type font files, right? Which are the ones that we see on Windows a lot. But there's also like Adobe Type 1. In fact, I don't know if you saw recently, Microsoft had a really bad hack involving Adobe Type 1 fonts where people could root your machine by including Adobe Type 1 fonts on the web, right? And there's been other types. There's Metafont is another kind, which was an old thing in LaTeX, right? There's a number of different types of fonts out there, font sort of file formats, right? And what these are ways of describing what the actual characters in fonts are supposed to look like, and they're usually described in terms of outlines. So typically, for example, like in a true type font file, for example, or Adobe Type 1 font file, typically what you're doing is you're doing something, if you've ever seen like Adobe Illustrator or something, you're typically doing something like that. So a typical font file might include something, like some vertices to describe like the letter T, right? They might describe something that looked like this, right? Where you were kind of saying, okay, we have some coordinates of some vertices, and we have some curves, in this case, not really curves, but lines that go into the vertices. And the way that we're going to describe the shape of the T is to say that we're basically talking about a filled area that exists within these points, just like you would, again, in Adobe Illustrator. And similarly, if for a curve shape, right, then what you're going to have is you're going to have something where you have points, and those points are going to have like Bezier curve handles or something like this, which we've talked a little bit about. I also have a video online about interpolation for Bezier curves, which is not really something we need to go over at the moment. We'll probably go over it a little bit later in Handmade Hero. But point being, they're like those things you see in drawing packages where you specify, 2 points and then 2 points that are sort of off of those points, and you kind of get these little handles, right? And then it draws like a curve based on the points and the handles, and like as you move the handle around, the shape of the curve changes, right? You might get something that looked like that. But again, it's the exact same concept as the lines. It's just saying, here's a filled shape, and we're going to fill it in. Okay? So that's the first part. That's the first part of what's happening in a font file, right? Is it's basically describing some filled shape that is from, for all intents and purposes, resolution independent. Meaning there's not really a notion of pixels here necessarily. There is a little bit of a thing called hinting, which I'll briefly mention, but we don't really care about it so much. But for the most part, we're not really talking about pixels here. We're just talking about an abstract shape. And that abstract shape could be scaled as big or as little as you wanted, and it would still be able to be infinitely precise because, again, it's not talking about individual pixels, it's talking about just that shape. So just like in Adobe Illustrator versus Adobe Photoshop, in Adobe Illustrator, you can make the shapes and you can scale them any size. In Photoshop, you paint on the pixels, and then that's, if you resize it, it gets blurrier or hard, right? It's the same deal, right? So we're talking about continuous shapes, not pixels. And the reason behind that is because people want to be able to ship one font file that allows them to use that font at any scale, right? You want to be able to ship, Times New Roman and be able to say, I want it 20 points, 30 points, whatever, right? And it gets bigger or smaller, just like you do, in any package that you use. So that's the first thing that they do, is try to describe a relatively resolution independent outline shape for the font that would allow a program that wanted to fill it in to fill it in. Now, the second thing that these do is they describe a mapping from some character set encoding to these outline shapes, right? And what do I mean by character set encoding? Okay, what does that mean? What I mean by character set encoding is that in the English language, right, or in Chinese or something, right, we all know what we're talking about when we say like the letter T, right, or the symbol for meat or something, right? I think it's got like a little, it's like something that looks like this, right, or whatever. I don't know, I'm trying to give an example in Chinese, but I don't speak Chinese, so it's hard for me. But anyway, there are these glyphs, right? And so the font file can describe this glyph. It can describe T, it can describe the symbol for meat, right, or whatever. But how do you know what symbol it's describing? Right? How do you know? We can't just give it, some arbitrary number like, okay, this is, glyph 17 in the file. Well, how do I know when I wanted to actually show the symbol for meat? How do I know that was glyph 17, right? And so the answer that we've come up with in the computing world is to have these character set encodings. And one of them you're very familiar with if you've watched Handmade Hero from the very, very beginning. In fact, I think it was maybe in the intro to C part. I don't know. I don't even know if we did it in Handmade Hero. It might have been even in the test thing where I did a little bit of C stuff. But basically, there's ASCII / ANSI encoding for characters. There's basically a character set encoding that allows you to do most like Roman-derived languages in a standard way, where we've basically just defined what all the characters are, right? We basically said, okay, if you're writing Spanish or English or French or something, we have mapped sort of in a definitive way that everyone has agreed to use, we have mapped all of the characters to some symbols. So we just know that O is 79. Right? Like that's just what we know. So inside the file, we could say something like, we are using an ASCII encoding. So when we tell you that this glyph corresponds, right, to, index 80 or something, we know that that's going to be, that's P, right? We know that that's P. So in the case I gave of T, we would know that we would put 84 as a numerical tag on this T. We'd say 84 is the T, right? And so the choice of character set encoding is very important because it defines what characters you even can encode. Now, for example, the symbol for meat in Chinese has no encoding in ASCII. You can't encode it. So if you were to pick a font description that only allowed you to use ASCII, you would not actually be able to include that character in your font. It just wouldn't happen because you'd have no way of even telling someone what it was. Now, what you could do instead is say, okay, you know what? I didn't really need this weird block shape that's like number 223 in extended ASCII. So I just said like, okay, that's going to be the meat symbol. And just in my game, I know to use that, right? You could do that. Another thing you could do is use a thing called code pages, which are like ways of switching out ASCII for a different set encoding that would only work in for like, say, Chinese or something. But again, you haven't really solved the problem. And with only 256 glyphs, which is all you're going to get out of ASCII anyway, you're not going to be able to do something like Chinese, which is going to have at least 3,000 symbols, even in a basic situation, and up to 30 to 40,000 symbols in the case of one that was supposed to encompass the entire, archival, ancient set where you were going back through all the symbols that have ever been used in Chinese lettering. Right. So what we have done recently is we've moved to a thing called Unicode as the more standard thing, right? This is kind of the older school approach. This is like the newer school approach, right? And what Unicode is Unicode is a way of encoding drastically more characters. It goes up to 16 bits in the naive implementation, like with Windows, a thing called UTF-16. And then it goes in UTF-8, which is a different encoding of Unicode. It actually can go above 16 bits. It can actually do more. And so, like, as we know on Animated Hero 65536, right, we know that 16 bits would give you 65,000 symbols. That's quite a few symbols. That's awesome. But UTF-8 allows even more because it's basically a variable length encoding where it's still 8-bit characters, just like ASCII is, but you can kind of double up the characters and say that like a particular character can say, oh, there's another character coming after me that combines with me to produce the actual value. And so you can kind of like chain them to be as long as you want at that point. So you can get up to 24-bit of the address space, which is, 16 million glyphs, right? So basically, Unicode is the way that we sort of broken through the ASCII table that was just 1 byte per character, that which was insufficient. So now what Unicode is, it kind of has a good and a bad to it, if you will. The good thing about Unicode is that every character has a unique identifier. Well, it's not quite what I mean to say, but all glyphs have sort of found their home in Unicode, right? So it doesn't matter what random language you want to do, even if it's one that like isn't even spoken anymore, right? Somebody somewhere, hopefully, has allocated some set of the Unicode mapping and said, here is where those symbols go, right? And what that means is a single font could literally, if it wanted to, describe all of the symbols that all humans have ever used to ever write anything down, like period, right? And that's pretty cool. But the problem with that is that you're stuck with that in giant encoding, right? So you can't just use a table that's 65K entries long or more, like 16 million entries long. That'd be a crazy huge table to use in your game of fonts, most of which would be 0 because your game isn't translated into Sanskrit, right? Your game isn't translated into all of these archival languages potentially, right? Your game just isn't going to use all those. You don't have the font for it anyway. You're never going to display them. So usually what ends up having to happen, and the thing that's a little bit nastier about Unicode, is typically you have to sort of treat Unicode as an intermediary mapping because your lookups cannot be dense anymore. So typically what ends up happening is you've got some kind of a translation process that you go through. So, if you wanted to use Unicode, it's typically going through some kind of a mapping to finally get you into a dense table of what does my font actually have in it? And that would be dense, right? So I have a table of just, this font has 500 glyphs in it, right? And Unicode is this gigantic, 24-bit address space or something, right? It's not actually 24-bit, I don't think, but, somewhere up there, over 16 bits of address space. I go through a mapping that's some way of crunching this down to actually get it to figure out where in this dense table of actual font glyphs I'm actually trying to look for the font glyph that I want. So it's just something to be aware of. Like Unicode just kind of has this nasty property of, because it's supposed to be a universal encoding that can describe any glyph, it's actually not very good for describing the glyphs that you have. So typically what you end up doing if you want to support arbitrary languages in a system is, yes, you accept Unicode as your encoding, but then whenever you get one and you want to actually start working with it to display something on the screen, you go through some kind of mapping that will put you into the right place in your table of glyphs you actually have, right? Okay, so back to our font files. So what the font file ends up being at the end of the day is typically something like a Unicode. Oh, and by the way, I didn't actually say it. They are called, this sort of entries into the Unicode table, they are called code points. So when you hear someone say a Unicode code point, they are referring to that numerical slot that has been reserved for this glyph. Slot 63,452, all right, which corresponds to whatever glyph. That's like a Unicode code point. That's typically what that phrase is used to describe, right? Yeah. So anyway, so that's typically what ends up being in something like a font file, is it will be something like, here is an outline of a T, here is the Unicode code point, right? That describes which glyph I'm talking about. So now the code knows, oh, okay, that's an English letter T. Okay, I get it, right? Or that's the Chinese symbol for meat, right? I get it. So now it's basically like a way of bridging that gap of, I've just got a bunch of outlines in this file. I need some way of telling you, what do they actually mean to a human who spoke this language? What do they mean? And that's what it tells you, right? So the code point is almost all the information we need. Almost all, right? We've got a glyph, we've got the code point, but it's not quite enough yet to actually constitute a useful font. And the reason is because we don't actually know how to start assembling multiple characters together into words. So let me tell you a little bit about basic typography here. I'm not going to harp on it because Handmade Hero is not about text, so we don't have to be expert typographers to do the implementation of the font system in Handmade Hero, right? If you were doing a game that was all about fonts, you would want to be an expert typographer, certainly. But I'll give you a little bit of the basics. So in typography, right, basically everything is about sort of the solids and the empty spaces and the solids of the fonts, the shapes they make and how they like interrelate. They spend a tremendous amount of time thinking all of this through. And they have a bunch of properties about fonts that they think about. So for example, you might take the letter G, and if you wanted to talk about that shape, there's a number of things that you could talk about. You could talk about the fact that, for example, the G, unlike the H in a standard font, you might say that the G has a descender in typography speak, which is this bit that comes below sort of the line here. And then you might say that the H had like an ascender, which is something that kind of comes up above this, right? There's ways that they describe these things. But this line right here is often referred to as a baseline, right? And so one of the things that is described oftentimes in a font file is what is that baseline and what are the characters how does the character glyph relate to that, right? How does the character glyph get positioned relative to the baseline might be a piece of information that's necessary in the font file, right? Similarly, something like what is the maximum descender height, right? Like of all of the characters in this font, what's the one that goes down the furthest? Of all of the ascenders, what's the one that goes up the highest? And again, these are things to allow you to know when you're going to go use this font, what is its general span vertically, and what is the actual region that it actually typically uses, right? What is, another one would be, what's the line height? Meaning, what did the fontographer who created this font envision being the spacing between lines in a normal scenario? Like, you know, if I was going to put the next character down here, where would it be, right? So you start to have some information like that. But most important of all, and unfortunately a lot of fonts just don't even do this very well, but ideally speaking, your font file has a thing called kerning. Kerning information. And what kerning is kerning is a way of understanding how to adjust the positioning of letters horizontally based on which pair of letters you're talking about. Okay? And so to understand the difference between these things, you first have to sort of think of the difference between mono and proportional, right, fonts, which you've probably seen before, right? A mono or monospaced might be the more appropriate term, right? Monospaced font. A monospaced font is the old school kind that was on typewriters and terminals when they did not have the level of sophistication necessary to advance the right position by a variable number of pixels or space on the typed page or whatever, right? And so what happened was a font just had to have an equal amount of space. So if I had a G and I had an I, they both had to take up the exact same amount of space width-wise, which looks pretty dumb. Because there's this giant gap on either side of the I, right? Because if you were to make it the size that you would normally want to make the I, the G would like sort of overflow it, right? So you kind of had to adjust it to make it some kind of uncomfortable size that was too big for some letters and too small for others, but you know, it kind of was like the best you could do, right? And so as you typed away, it would just move by that amount, and you would end up with something like the word Gill would look something like that, right? Where the spacing was consistent between each of the center points. And it would look really stupid because the way that fontographers who laid it out in lead would have done it would be like that, which looks a lot more natural and is easier to use, and also helps articulate the difference between spaces in between letters, which are not what you want to focus on when you're reading, and space in between words, which you do, because it helps you tell, right? Words are recognized kind of as a chunk, and so you want them to group together cleanly and not have the person be confused about what is the space and what is the word, right? That's not a good thing from a typography standpoint. Okay. So once we had the sophistication to do so, proportional fonts were definitely a preferred thing to do because they were certainly better than monospaced fonts for readability, and so systems wanted to support that so they could produce better looking output that was more on par with what typographers were able to do, because they had refined that in sort of the printing press style, right? They were making characters that were different sizes already. And so what we wanted to do is we wanted to, in computing, we want to be able to do that same sort of stuff. And so what we can do is we can say, okay, now whenever we draw a glyph, when we draw the next glyph, we'll just sort of have some understanding of how far to go. But if you think about it, it's actually a pretty tricky problem because the actual distance you might want to go is not necessarily constant depending on the letter. Right? A naive proportional font implementation just says, okay, for every letter, there's a certain distance I will advance, right? And that's fine in general, and it solves our Gill problem to some degree, right? But what it doesn't solve, and what's sort of a level above that, right, is the concept that depending on which two letters you were putting back to back, you might choose a different amount of space. And to give you sort of an example of how that works, right? Suppose I was to take the letter G and the letter J, right? And I was going to put those two characters next to each other. Well, I would probably want to space them so that there's like a reasonable amount of space here, which would leave kind of more space there, right? So when I'm thinking about how close this J should be to something, I have to consider that, right? It's going to be a little bit different there. Now, on the other hand, if I had an I, right, and a J, those could go much closer together because the J descender can easily overlap the I, right? The same thing would be true in the forward direction. That was kind of a backwards looking kerning example. The same would be true in a different example. If I have an F, right, and I'm going to follow it by an H, right? I guess I drew my F kind of poorly. If I have an F like that, right, and I'm going to follow it by an H that goes all the way up, right, like so, I would probably have to space these so that, it looks something like that, which leaves a fair bit of space here, but, it's because of the closeness there, right? Again, on the other hand, if it was an I could probably snuggle that I in right next to it. In fact, this is so common, there's even a thing called a ligature, which we don't really have to cover in Handmade Hero, but there's a thing called a ligature, which is actually when the fontographer creates a unified glyph designed to represent F and I together because it's so common, and oftentimes they'll do it. It looks like that. It's like a combination of an F and an I, right? So yeah, the point being, the distance between letters can be highly dependent on the pair of letters, not just the letter that came first and advancing by a certain fixed amount. And so that's where kerning comes in, which is the idea of modifying the inter-character spacing to account for that pairwise difference. And so what you end up having is you have another lookup table in this font file, or I shouldn't say a lookup table because it's just encoded, information encoding in the font file, right? Which would be something like, a simple example would be something like this. It would say, you know, a character A, character B, or I should use something else, character 1 and character 2. I don't know what to say. Character, I can't use anything because any glyph is going to be something that could be in there. Character A and character B, and then a kerning value. So it would say like, okay, if there's a G and a J that are back to back, I want you to do, you know, the spacing is 5. If it's instead an I and a J are back to back, I want the spacing to be less. It's going to be a 1, whatever. And oftentimes the way that kerning is represented for encoding reasons is that typically it's actually not the total amount of spacing. That's really not what they tend to encode. Kerning typically refers to the delta between the normal spacing and this pair spacing. So typically what will happen is you'll say, okay, there's a normal spacing. There's a normal advancement, right, for a G. So in the table where the fonts are encoded, we say G advances 10 units, right? That's what G advances. And the kerning for GJ would say, okay, you were going to advance 10, now subtract like 5 from it. So you actually just do 5. So instead